seconds if you want to start.
Yeah.
Sure.
Okay. Good morning, everyone. Welcome to the oral session, the morning oral session on low-level vision. We have 13 amazing talks today. Before the talk starts, I want to remind everyone that we can also ask questions through the Slido website, or you can download the app. And let's get started. Maybe the first presenter.
So as you know, the talks will be in groups of 3 talks, each 5 minutes. And after that, there will be 3 minutes Q&A.
So morning, everyone. Today we will introduce methods for perception-distortion trade-off in single-image super-resolution. So single-image super-resolution aims to restore a high-resolution image from low-resolution one. Some methods only aims to improve the object quality, while some methods aim to improve the perceptual quality. So if we draw these methods in a perceptual distortion plane, we can see that the methods driven by object quality usually with poor perceptual quality, while the methods driven by perceptual quality can generate photorealistic images, but with very low PSNR. So recently, there have been some methods which aims to achieve a trade-off between these two, like the SR-GAN MSE. So in this work, we aim to further push forward the trade-off between the perception and distortion. If we aim to super-resolve an image which has both high objective and perceptual quality, the intuitive solution is to train a neural network which minimizes the combined loss of MSE, perceptual loss, and the GAN loss. However, this may lead to unstable training and also some twisted structures in the restored images. Okay, here we have 2 very important questions to be answered. That is, what elements influence the object quality and what elements influence the perceptual quality? To answer this question, suppose that we have these 3 images, AP with high perceptual quality, AO with high object quality, and the ground truth. So we apply stationary wavelet transform on these 3 images, which can decompose each image into one low-frequency subbound and several high-frequency subbounds. Okay, now we can see this very interesting phenomenon. The high-frequency subbounds of image AP are quite close to those of the ground truth, and the low-frequency subbounds of image AO is close to the ground truth. So is this the reason why AP has high perceptual quality and AO has high object quality? To verify this, we just switch the low-frequency subbounds of these 2 images, and then we reconstruct the image using inverse SWT. And we can see the object quality is changed a lot. However, the perceptual quality is not influenced too much. Okay, now we have this very important observation. That is, low-frequency subbounds contribute more to the object quality, while the high-frequency subbounds are important for the perceptual quality. And based on that, we can have a possible solution. That is, we can pursue high object quality at the low-frequency subbounds and high perceptual quality at the high-frequency subbounds. However, if we do so, we can still have some problems. That is, the high-frequency subbounds may exist some messy structures, as we show here. So how to solve this problem? Okay, so we can have access to these 2 images very easily. And we found that AP has twisted structures, but AO has correct structures. So we are wondering whether we can rearrange the structures in AP with the guidance of AO using style transfer. Well, the answer is yes. So we have these 2 images, right? And they will perform SWT on them. And for each high-frequency subbound pair, we apply wavelet domain style transfer to generate a new subbound. So like the traditional style transfer, we have a content loss, a style loss, and a new added wavelet regularization loss, which aim to generate a sparse wavelet subbound. All right, so after style transfer, let's see whether the problem is solved. Okay, we can see that after style transfer, the messy structures have been corrected successfully, and also the details are preserved. So for reconstruction, the low-frequency bounds can either be directly from the image AO or through an enhancement network, which further improve its object quality. And then we reconstruct the image using inverse SWT. So here are some experiment results. We can see that we achieve quite good trade-off between perception and distortion. And here are some dynamic examples which show how we correct the messy structures. OK, thank you for your listening.
Good morning, everyone. I'm from the Hong Kong Polytechnic University. I'm going to introduce the work toward real-world single-image super resolution, a new benchmark and new model. This work is supported by DJI and Alibaba DAMO. Significant progress has been made in recent years. However, most of the models are trained and evaluated on simulated data sets. They may not be able to generalize well to real data, because the degradations between them are different. Here we show an image captured by a camera. When the models are trained on simulated data sets, they cannot effectively recover the details. In contrast, when the models are trained on a real-world data set, they show much better results. In this work, we have two contributions. First, we build a real-world super resolution dataset, which consists of precisely aligned HR and LR image pairs with different scaling factors. Second, we present a Laplacian pyramid-based kernel prediction network to learn spatially variant restoration kernels for real SR. To construct the real-world dataset, we use zoom lens to capture image pairs at different focal lengths. From the equation, it's easy to derive that the image size H2 is approximately linear to F. By increasing F, larger images with finer details can be recorded in the camera sensor. However, the zooming of the lens brings many changes, including the lens distortions, exposure, color, and shift of the optical center. We thus develop an image registration algorithm to progressively align such image pairs to build our dataset. This figure shows our registration process. We first import the images with meta information into Photoshop to correct the lens distortion. We then crop the interested region around the center of the image, where the distortion is not severe and can be well corrected. The cropped region from the image taken at the largest focal length is used as the ground truth HR image. The LR image is registered from the image taken at a smaller focal length. We develop a pixel-wise registration algorithm which iteratively estimates the luminance adjustment parameters and the affine transformation matrix. Finally, images that cannot be precisely aligned are discarded. Our final data set contains hundreds of images taken by 2 cameras and 3 scaling factors. In the conference version, we have about 250 scenes. Now we have an extended version with more than 500 scenes. As we have mentioned, the real-world degradation is spatially variant, so instead of directly learning an image-to-image translation, it first predicts per pixel kernels and then apply the predicted kernels to the input image. However, this introduces a problem. The size of the per pixel kernels grows conjecturally with the kernel size k. This can result in heavy computational and memory cost when the image size is large. To solve this problem, we propose the Laplacian pyramid-based kernel prediction network. We employ the Laplacian pyramid to decompose the input image into several levels of sub-images, which have different downsampled resolutions. At each level, our model predicts a specific kernel for each location of the image. Finally, the Laplacian pyramid reconstruction is performed to get the output image. This effectively reduces the computational and memory cost of KPM. In this table, we compare 3 models trained on simulated datasets and our real dataset. As can be seen, models trained on simulated datasets obtain unsatisfied performance on our real-world dataset. This validates that the real-world dataset is necessary. In this table, we compare the proposed LP KPN model against the other models. We can make two observations. First, when using similar complex architectures, KPN improves performance. Second, LP KPN achieves comparable performance using much smaller kernels than KPN. We also did a cross-camera evaluation and found that models trained on one camera generalize well to another. Here is an image taken by mobile phones. We can see that LP KPN trained on our real data set obtains better visual quality. For more information, please come to our poster. Thank you.
Hi everyone, I'm Wenlong Zhang from Shenzhen Institute of Advanced Technology. Today I'm going to introduce our work on generative adversarial network with ranker for image super resolution. Traditionally, super resolution is defined as a reconstruction problem, and PSNR is used to do evaluation. However, PSNR cannot tell everything. Generation approaches can generate realistic textures with lower PSNR. Then researchers find that there is a trade-off between human perception and distortion. The generation methods can achieve better perceptual quality at the cost of PSNR value. So here comes a problem: how to evaluate the perceptual quality. RMSE is often used to evaluate reconstruction methods, but it has a weak correlation with perceptual quality. Furthermore, the perceptual index, which is proposed by Pier and Munchurl, is highly correlated with the perceptual quality. As we can see from the pictures, the lower NIQ values, the better human vision that we can achieve. However, most of perceptual metrics are not differentiable, that include handcrafted feature extraction or statistic regression operation, so it cannot directly to serve as optimization objective. To address the problem, we propose a ranker to simulate the behavior of a perceptual metric. Then we can optimize the generator in the direction of perceptual quality. The framework involves three stages. The first is to generate a ranked dataset, and then using the ranked dataset to train a Siamese ranker. Finally, we introduce rank content loss to get the training of generator. For ranked dataset, we use three SR methods to generate the SR images. Then NIQE metric is used to generate rank label. The image with a high NIQE value is regarded as rank label third, while the lowest is set to rank label first. Here are three samples. The rank label only related to the order of NIQE metric, but not the real values. Finally, we randomly pick up two of them and compose a rank pair for training ranker. Then we use a Siamese network as ranker and margin ranking loss for training. Specifically, the ranker output the ranking scores instead of the real values. As we can see, the regression outputs tend to learn NIQE label, while ranker can enlarge the distance of different levels. Furthermore, we define a rank content loss to optimize the generator in the direction of the given matrix. The fixed ranker can produce a ranking score for the output SR image. Then the gradients can be backpropagated to the generator. Here are the experiments. As we can see the NIQE convergence curve. We find that RankSRGAN is consistently better than SR-GAN. For PSNR, it also achieves comparable performance. Compared with other SR methods, RankSRGAN achieves the best NIQE and the PI performance on all tested datasets. And we also provide some visual results, and it can generate more realistic details with the lower NIQE value. To validate the effect of different ranked sites, we use ground truth HR image instead of SR-ITM images. We can see RankSRGAN with a better ranked site can improve the results of base model. Then we use different perceptual metrics at the rank level. All other settings remain the same as RankSRGAN with NIQE. We find that RankSRGAN can generalize well on different perceptual metrics. In addition, we test the balance between MSE and rank content loss. The results show that adjusting the weight of the loss could operate the trade-off between NIQE and the PSNR. Well, our post number is 18. Welcome to discuss with me. Thanks very much.
So if you have questions, please come to the mic.
We have 3 minutes to any of the three talks.
So there's one question from the Slido. I think to, it doesn't specify, I think it's to the third paper.
No, first paper. It says first paper.
The question is it possible to construct a metric to measure quality of super resolution according to first paper's research?
For me, if you would like to construct a metric to measure both the object quality and perceptual quality of an image, it's a little bit difficult. But the possible solution can be you can divide the image into, let's say, low frequency and high frequency subbounds. And then for each subbound, you apply either objective or perceptual. So for the objective, for the low frequency subbounds, you can apply the objective metric. And for the high frequency subbounds, you can apply the perceptual metric. And then, yes, I think this can be a possible solution.
Any questions? Any other questions for the author?
With the presenters for the second group come up to those three chairs.
So I have a question for the third speaker. So when you do the rank, in super resolution, you may have some regions that have different rank than other regions. How to deal with that when you construct a rank database? Some algorithms may perform in certain regions than other regions, right? Than other method.
Yeah, our work, the key point of our work is to optimize the perceptual quality. So we create a ranked site using SR-ITM, and SR-GAN to simulate the behavior of perceptual metric. So it can add a bridge to construct the behavior. Thanks.
Okay, maybe I can discuss with you later.
Yeah,
of course.
Okay, it's about time. So.
Yeah, any other question? If not, let's thank our speakers.
Okay. So we'll start the second group. Please, the presenter for the fourth talk, please come up. Yeah, it's time.
Hey everyone, we present the paper Progressive Fusion Video Super Resolution Network by exploiting non-local spatial-temporal correlations. As you can see, video super resolution aims to reconstruct high-resolution video frames from the given low-resolution video frames. Here, we give 3 fusion strategies used by most space-based video super resolution methods: direct fusion, slow fusion, and 3D convolution. Direct fusion fuses frames into one part directly, while slow fusion does it gradually. 3D convolution networks conducts convolution in both space and time dimensions. In this paper, we have designed a progressive fusion residual block, whose structure is illustrated on the right side. Take 5 frames for example. We first conduct convolution on the first layer, to extract rather self-independent features. Then the second layer of feature maps are merged into one whole part, which contains a large deal of temporal correlated information. To extract a more concise information, we use a convolution to reduce the dips to a basic number. After that, this distillated feature map is concatenated to all previous second layer of feature maps to form the fourth layer of feature maps, each of which consists of two kinds of information: self-independent spatial information and fully mixed temporal information. The fourth layer is further convoluted and added to the first layer to form the final output. Overall, both intra-frame spatial correlations and inter-frame temporal correlations are fully extracted progressively. Further, the multi-channel design enables us to conduct parameter sharing across channels within one residual block. Traditionally, a lot of video super-resolution methods conduct explicit motion estimation and composition to increase the temporal coherence of input frames. Inspired by non-local neural networks, we introduced and improved the non-local residual block to suit the video super-resolution task. For generation tasks like super-resolution, the input size can be arbitrary and remarkably big. Consequently, we make several improvements to make it cost less GPU memory. First, we reshape the input, transforming the temporal dimension into the channel dimension. That is to say, the temporal correlations are captured through the channel correlations. Second, we introduce a rescaling factor R, transforming part of the spatial dimension into the channel dimension. We compare the proposed non-local residual block with two kinds of motion estimation and composition methods. As illustrated, the effectiveness of STMC and SPMC are limited, while non-local residual block increases the performance obviously. We further give a visual comparison between these models. As you can see, flickering artifacts can be found in VSR, VSR STMC, and VSR SPMC, while the result of VSR NLR2 is smoother. We then confirm the validity of the proposed progressive fusion residual block. We first design a base network denoted as PFS. For fairness, we design other networks, DFS, SFS, and 3DFS with similar number of parameters. As you can see, PFS achieves the best performance with a relatively fast speed. We then adopt a parameter sharing scheme to these networks. It is observed that DFS, SFS, and 3DFS suffer a considerable drop in PSNR by sharing the parameters, whereas PFS still remains a good performance. Our network is remarkably efficient, which requires about 3 million parameters, and it costs about 741 milliseconds for testing and 17 hours for training. Our network achieves the best performance on video set 4 and UDM10 datasets. Here we give two visual comparisons. Our network generates clear numbers and red texture. Thank you.
Good morning. This is Soo Ye Kim. I'll be presenting Deep SR-ITM, joint learning of super resolution and inverse tone mapping for 4K UHD HDR applications. This is a joint work with Jihyong Oh and our advisor, Munchurl Kim. I'll first explain the motivation to this problem. Ultra-high definition televisions, UHD TVs, are being rapidly deployed in consumer markets, and these UHD televisions also tend to be HDR, high dynamic range. However, one problem here is that there is a severe lack of the original UHD HDR videos and an abundance of the conventional HD high-definition, SDR, standard dynamic range videos to send out in the transmitting side. And this is where joint super resolution and inverse tone mapping comes in. Individually, super resolution upscales low resolution videos to high resolution, and inverse tone mapping upconverts standard dynamic range videos to high dynamic range. Note that the produced HDR videos here are not luminance maps nor radiance maps, but they're videos in the HDR display format with a higher bit depth and a wider color gamut. And so SR and ITM jointly combined enables the direct conversion of 2K SDR videos to 4K HDR. There are two important aspects in this joint problem. Firstly, the spatial resolution must be increased while restoring the lost high-frequency details. And secondly, the signal amplitudes must be increased while recovering the local contrast. This is because as the pixel range increases, there's more room for local variations. So we've considered these two aspects when designing our network architecture. Now focus on explaining the two main features of our design choices. Firstly, it's input decomposition. So when a low resolution standard dynamic range image is entered into the network, it is first decomposed into the base layer and the detail layer. The base layer contains overall brightness and color information, while the detail layer contains high-frequency details, such as edges and texture. The feature extraction passes proceed separately for these two layers, and each of the layers is able to focus on the input it's provided with, leaving the detail layer to focus on the high-frequency components of the input image. The second element in our design is the feature modulation blocks. For the two main feature extraction passes for the base and the detail layers, there are also modulation branches for each of the passes. The corresponding input goes through the shared and independent convolution layers to produce the modulation maps in each modulation block, and they are element-wisely multiplied onto the output feature maps. In convolution operations, the exact same convolution filters are applied on all locations of the input in a sliding window manner, which is inappropriate for enhancing local contrast, which is different depending on the local region. Therefore, these element-wise multiplications introduce spatially variant operations for location-specific contrast enhancement. The quantitative results were compared with the only joint SR-ITM method and also the cascade of existing super resolution and inverse tone mapping methods on 5 different metrics for 2 different scale factors. Our proposed deep SR-ITM outperforms the other methods. Here's an example video comparison against the cascade of existing methods. You can see that the proposed method shows enhanced contrast and better details, especially in the edges and texture. Here's another video in a darker environment. And again, deep SR-ITM shows enhanced contrast and is closer to the ground truth. All relevant codes and data are released on GitHub, and please visit us at poster number 20 for any further discussions. Thank you.
Hello everyone, I'm Yokota. The title of our paper is Dynamic PET Image Reconstruction using Non-Negative Matrix Factorization incorporated with Deep Image Player. PET is a technique for observing biomolecular mechanisms in the body. First, radioactivity tracer is induced in the human body, and we scan the target area such as brain by PET device. After scanning, we obtain the tiny series of sinograms. The task here is to reconstruct dynamic PET image from sinograms. Dynamic PET image
represents the spatio-temporal distribution of the concentration of radioactive tracer. PET imaging can be considered as an inverse problem. Observable sinogram Y is mathematically formulated by the radon transform of PET image Z plus noise N. The task here is to estimate Z from Y and P, but this is a very irreversible problem because of noise. Here, the prior is useful for robust PET imaging. For example, noise priors are important, such as Gaussian, Laplace, or Poisson distributions. Also, image prior is very important, such as smoothness. A typical example is combination of Poisson noise distribution like TB prior. We minimize K divergence and TB norm at the same time. The deep image prior is a novel image prior, which is included in free convolutional neural network architecture itself. In DIP, we do not use training set, but we use only ConvNet architecture for the priors. For static PET imaging, we minimize the K divergence between sinogram Y and radon transform of output of ConvNet. The procedure is the following 3 steps. First, we randomly initialize the weight parameter of ConvNet. Second, we iteratively update the weight parameter by gradient descent to decrease K divergence. Finally, we stop iterations at some appropriate point. So here we can see the noise was successfully reduced by early stopping in appropriate point. The question here is dynamic DIP is nice to be applied directly for dynamic PET. The answer is no, because dynamic PET has other interesting data structures. In this study, we assume dynamic PET has a low-rank non-negative metal factorization. In NMF formulation, PET matrix is decomposed into non-negative spatial bases and non-negative temporal bases. And we assume that each spatial basis has exclusive relationships with each other, and each spatial basis is generated by deep image prior. Finally, we assume temporal bases should be smooth. This is the optimization problem of the proposed method. All priors are included in optimization problem, and we solve it by alternating optimization framework. This is the optimization behavior of the proposed method. 3 uniform noise are inputted into ConvNet, and 3 ConvNet output the spatial basis. And the smooth temporal basis is also optimized and integrated into reconstructed dynamic PET. It's radon transform reconstructed the dynamic sinogram, and its K divergence is minimized. The early stopping at 5,000 iteration is good in this case. This is a quantitative evaluation by using phantom dataset. So we can see the proposed method is much robust than other existing method. This is a result of clinical dynamic PET reconstruction. So we can see FBP and EM suffer from noise, and TB regularization obtained blood images. By contrast, the proposed method is much better than others. This is a result of blind brain segmentation by using proposed method. This is somewhat promising because, look here, the brain basal ganglia were automatically extracted without using brain anatomy. Thank you for your attention. Please come poster and enjoy Python code in GitHub. Thank you.
Thank you. Will the presenters come up? Is there any question from the audience? There's a question in the Slido to the first speaker. Concatenation of time in channel forces a fixed time window.
Pardon?
Concatenation of time in channel forces a fixed time window. Yes, if you want to. Here. This one, this here. question goes, what effect does the window size have?
In fact, we have explored 3 different window sizes, 3, 5, and 7. That means the input frames. And we have found that more input frames will bring more supplementary information, and the network will behave better with bigger window size.
Okay. Is there any other question?
Yeah, I have a question. I'm raising my hand over here.
Okay, go ahead.
Hey. So this is for the second paper. So first, it's very nice work. It's very nice to see somebody doing super resolution and also considering the bit depth.
Thank you.
So I have one question about how you did your training data. I didn't quite catch it. So do you have, you start with ultra high definition video and downsample it,
yes,
the standard?
Yes? So, yeah, okay. Yeah.
Is the answer yes?
I mean, no, it's, so the question is on the training data, right?
Yeah, but, so my question is, if you do start with ultra high definition video and then you downsample it, is there a standard procedure for that? Because you do have a lot of freedom going from that higher gamut to the smaller gamut. So I'm just curious if that's the way you do it. Is there a standard procedure to do this?
So going from 4K to 2K, we use bicubic downsampling, which is common practice for super resolution methods. And then for going from HDR to SDR, we were actually using the commercial software by YouTube. So because we tried out like 19 different TMOs, tone mapping operators, to go from the HDR videos to SDR videos. But they showed some artifacts, especially in darker images or other.
Right.
Yes.
But so, HDR and SDR share the same color space, but UDH is a different color space. So when you downsample, you have to think about this, going from a higher gamut to a lower gamut. So right now you just bicubically downsample.
So for when we meant HDR, we meant the BT 2020 color space.
Oh, okay.
Yes, and then SDR was in BT 709.
Okay.
So yes, so we were just automatically converting using YouTube.
Thank you.
Okay, thank you.
Is there any other question in 10 seconds? No? Okay.
Oh, there's one question from Slido. I think for the first paper, whether the unsupervised pre-training data set with raw image, is that public? The unsupervised pre-training, is the data set with raw images public?
The data set is public, but we use supervised training data set.
Yeah, so it's available?
Yes.
Okay.
Okay, let's thank the 3 speakers.
Just a reminder, if you are going to submit a question, please clarify which paper you are referring to in the slide.
Good morning. My name is Jerry, and I'll be presenting deep stereo image compression along with Shenlong Wang and Raquel Ertson. So just to give a little bit of motivation, many application settings involve the use of stereo image pairs, and they often take up a ton of data per day. So we want to be able to compress these stereo images to reduce their storage while maximizing the quality of these images. And the key challenge is how can we utilize this shared information between them to our advantage? So in terms of prior work, there's single image compression, including codecs such as JPEG and BPG, as well as deep learning approaches. And they typically encode an image into a set of discrete symbols through linear transforms. There's also video compression approaches like H.264, H.265, and also deep learning, and they typically exploit the temporal redundancies within a video sequence by encoding the first frame independently and then encoding the flow and residuals for subsequent frames. So in our approach, we try to focus on the stereo image compression setting. And so we designed a novel architecture for the task of compressing stereo images. And we achieve a 30 to 50% reduction in the second image bitrate at lower bit rates compared to compressing the images separately with single image compression. The key insight here is that the information from the first image should both improve the reconstruction of and reduce the bitrate for the second image. And our proposed solution consists of 2 complementary key novelties: parametric skip functions at the feature level and a conditional entropy model at the entropy level. And we'll explain what these things are in just a little bit. So overall, our architecture consists of 2 encoder and decoder copies inspired by the Ballet single image model in 2018. Then we feed features from the first encoder and decoder to the second through these things called parametric skip functions. So let's take a deep dive into what these things actually do. These parametric skip functions are at every single level of the encoder and decoder. And they predict a disparity map at a given resolution to capture the feature correspondences between the cameras. Then using this disparity map, we warp the feature from the first encoder and decoder to the camera of the second before feeding it into encoder and decoder 2. The second part of our model is a conditional entropy model, which is a probability model modeling the joint distribution of the 2 image codes. So this is important because there's a step in compression called entropy coding, which losslessly compresses these discrete symbols into a bit stream. And entropy coding typically requires some sort of probability model. And the better we can predict these symbols with high probability, these latent symbols, then the lower the joint entropy of the image codes, and hence the lower the bit rate of the image codes. So our approach, we try to maximize the probability of the second image code Y2 by making it dependent on the first Y1, as well as on hyperprior codes Z1 and Z2. And this reduces the joint entropy of both image codes and hence the overall bit rate. Our data set consists of an internal self-driving data set called North America, as well as cityscape stereo pairs. Now, in terms of quantitative results, we plot the rate distortion curve, where distortion is measured by MSIM, taking into account the structural quality of the reconstruction. And this curve higher is better, and we can see that our gray curve outperforms image encoding baselines such as BPG and the Ballet model. It also outperforms residual encoding baselines, which take into account the motion compensation and residual coding techniques from video compression. Now, in terms of qualitative results, we see that compared against the single image Ballet model, our approach produces results that are slightly sharper and, more importantly, require fewer bits. And so you can see that in the magnified green crops in the images above. And in the second image, you can see that the detail of the trucks are slightly magnified in our approach, but more importantly, we achieve a bit rate reduction in the joint bit rate. Compared against BPG, our approach demonstrates a more even quality of detail, whereas BPG tends to blur certain regions while magnifying others. And compared against a residual coding baseline, which again uses motion compensation and residual coding techniques from video compression, our approach doesn't demonstrate artifacts or tears, whereas the other approach does. Great, thanks, and come check us out at poster number 22.
Hello everyone, I'm Eugene. This talk is about variable rate learned image compression with a conditional autoencoder. This talk is done with Mustafa El-Kami and Zhang Lee in Samsung. Learned image compression recently advanced to perform classical image compression codecs like JPEG and BPG, which is designed by domain experts. There have been 2 approaches in deep learning-based compression schemes. Autoencoder-based one showed the state-of-the-art performance, but it had been needed to train and deploy separate networks for different target rate to vary the rate. So it's not that practical. So RNN-based model vary the rate with one network by progressive encoding and decoding, but it showed worse performance than autoencoder-based models. Basically, our approach takes the autoencoder architecture while adding some conditional variables to that to control the rate with one model, so it can make good performance and also become more practical. So autoencoder takes X, the input image, and encode it into some latent variable Y, and it quantize it to G. So we basically compress G into some binary files. So there are 2 competing measures in compression. That is distortion and rate, and they are optimized in a Lagrangian form. So in our framework, we introduced 2 control parameters. One is Lagrangian multiplier, and the other one is bin size, which are given as the conditioning variables to the model as shown in these figures. So conditional autoencoder is implemented with conditional convolutions, which take the Lagrangian multiplier as an additional input. So the scaling factor and the bias of the conditional convolutional output are now function of the lambda, so the final output becomes depend on the lambda. For tractable rate estimate, so we adopted two relaxations. One is continuous relaxation using universal quantization, and the other one is variational relaxation. So universal quantization is used to induce source-independent uniform noise instead of adding noise artificially. So we observe some performance gain from this modification, as shown in these figures. And we train actually one conditional model for mixed Lagrangian multipliers and mixed bin sizes. And here the pair of values for lambda and delta plays the role of the correlative factor as in JPEG or BPG. So at inference time, the coarse discrete rate adaptation is done with varying lambda, and fine continuous rate control is done with varying delta. So we implemented this idea with hierarchical two-stage autoencoder with autoregressive priors. Here is some details. And we compare our method with the previous work, and our method performed comparable to the state-of-the-art learned image compression schemes, but we emphasize that we only train one model and use one conditional network to obtain the whole RD curve, while the previous method trained many networks to obtain each point in the figure. We also compared our model to, we also trained our model for different distortion measures like MSE and SSIM. So we trained multiple fixed rate models to compare them with one variable rate model. So you can see that the loss of using one conditional model is very marginal. So finally, I show some examples how the rate-term variable and the number of bits assigned for rate-term variable changes as we change the lambda and delta. So you can see that the rate-term variables become sparser, and the number of bits assigned for rate-term variable also becomes smaller as we increase the lambda or delta control parameters. So in conclusion, we developed variable rate learned image compression framework with a conditional autoencoder. So introduced conditional convolution and universal quantization in this scheme. So it achieved comparable and sometimes better performance than the previous method, which requires multiple networks to train the models. And finally, this framework can be used to solve other constraint optimization problems with deep learning. Thank you.
Real image denoising RidNet is a new single-pass network for denoising via feature attention. I'm Nick Barnes from the Australian National University. This is joint work between myself and Saeed Anwar of Data61, who unfortunately cannot attend. Denoising seeks to remove noise corruption, for instance, that inevitably occurs during image acquisition. In denoising, every observation incurs uncertainty, but not limited to a single photograph. There's also noise examples in flash, no flash pairs, blurry, noisy pairs, and stacked denoising. In every case, the aim is to produce a restored, clean image. Current image denoising networks employ two-stage models. First, predicting noise variance, and then using that prediction to remove the noise. We present a state-of-the-art model that uses only a single pass. It's the first work to introduce feature attention to wave channels for denoising. Synthetic denoising is near its empirical limits. We provide extensive results on real image denoising, where we show better results on complex images. In this example, our results show better performance than the previous state of the art. See particularly the colour artifacts on the face. Our overall architecture has a single feature extraction layer and uses 4 enhancement attention models before finally reconstructing the image. Our single-stage model uses skip connections at each step. In this image, you see long skip connections as shown here. Each of the 4 enhancement attention modules is embedded with a short skip connection and has 4 stages inside, each with a long skip connection. So within each of the enhancement attention modules, we have 4 parts. The first part of this is a merge and run step that branches features through 2 dilated convolutions in each branch, giving parallel multi-resolution paths for a feature pyramid. These are then rejoined with a concatenation and a convolution. This is then followed by a residual block with 2 convolutions to learn the features. Next is an enhanced residual block with 3 convolutions, including a 1-by-1 bottleneck. Finally, a feature attention block weighs the important features. Feature attention that we use here is similar to the standard approach of global average pooling, channel reduction, and upsampling, finally weighing the featured channels from the earlier stages. Our results are state-of-the-art over many datasets as detailed in the paper. Here we highlight 3 real image datasets, including the complex real scenes from the online benchmarked Darmstadt noise dataset. Here we can see better texture preservation compared with CBDNet. NII is commercial software that's part of Corel, PaintShop, and Photoshop. We show a significant improvement over NII. The smartphone image denoising dataset is a new dataset of photos from modern high-quality mobile phones. It shows more variation in terms of noise than DND. We show images that remove noise with less artifacts, resulting in images that are also clearly qualitatively closer to ground truth. The text is more clear and the noise is removed to a greater extent. In a second example from SIDD, FDDNet, a recent method, is unable to remove the noise. CBDNet replaces noise with a color cast artifact. The color cast problem is where a usually unwanted color affects the photograph evenly over a region or the whole image. Only our approach shows noise removal and consistent color. RNI is a real image dataset without ground truth. Here we show better noise reduction with smooth results versus DNCNN and FFDNet, which are both recent state-of-the-art approaches. So, RIDNet enables end-to-end training and testing for real image denoising, denoising in real images, It also allows for the weighting of features and leads to significant improvement over the current state-of-the-art. Our code's available on GitHub, and I'll be at poster station 24. Thank you.
Questions? If you have questions, please go to the mic. There are 6 mics here. So while people are thinking about questions, I have one for the first paper. Do you consider how to extend that idea to compress stereo video?
Yeah, it's definitely a really good point. I mean, I think the architecture right now is tailored to kind of, I guess, squeezing as much information out of the first frame to help the compression of the second. But you could kind of imagine a case where in a multi-view setting, it's not just dependent on like the frame next, like the stereo frame, but also on previous frames in a video sequence. So you could kind of, it's definitely an interesting area of research.
Okay.
I can ask a question again.
Okay, okay.
This is for the last paper, for Nick's paper. So first, your results are very nice. It's really impressive. One question I have is, do you retrain your network for each data set? Because some of the data sets are sRGB and some of the data sets are in RAW. So do you just train at one time and it generalizes to the different data sets, or for each data set you retrain?
I'll have to pass that question back to Saeed, I'm afraid. Sorry, Michael.
Yeah, but my guess is you retrain on each one. That's usually what people do.
Yeah, possibly, yeah.
Okay.
Any other questions? So I have a question for the second one as well, second paper. It seems very interesting. So it remind me about a recent work about this slimmable network, which can change its size during inference time. You train one model, but it can change different size according to computation cost.
Okay.
So I'm thinking whether you can incorporate that thought in your variable. It's well verify. Vary the size of the network based on the compression rates.
Sure, yeah, I think that's an interesting idea, and it's doable with our framework. So basically, we can make the network to be conditioned on the input for some computational cost, and then make the network to be slimmable or fat based on the input. Yeah,
so right now, the computational cost will not change for different rates, right?
Right, yeah, right, yeah. So
okay.
I think it's kind of a similar problem, yeah.
Okay, thank you. Any question? Okay, let's thank our speaker again.
Just a reminder, you can also ask questions through the Slido website. Okay, will the speakers for the last talks come up to those chairs? And the first speaker, please. So we have 4 papers for the last group.
Hi, my name is Marcus Brubaker, and today I'll be presenting noise flow, noise modeling with conditional normalizing flows. Excuse me. Oops. Sorry. Okay. Images taken by cameras are the main ingredients for computer vision. However, they're often corrupted by noise, and accurately modeling image noise can be an important step to improve a number of low-level computer vision tasks, such as denoising, multi-image super resolution, and others. So to start considering this problem, we're going to start by looking at a real camera image, shown here. Now we can obtain a clean version of this image and subtract it in order to see the resulting noise distribution. The noise might initially look to be Gaussian, but if we look more closely, we see that it's actually signal dependent. This is as would be expected based on the known Poisson distribution of photon counts. Right? So we see the signal dependence here in terms of the structure. Standard signal-dependent noise model scales variance linearly with underlying tensing, but this is not sufficient on its own given that there are many noise sources and nonlinear transformations that affect the observed distribution. It's difficult to model all of these sources, and instead we propose in this work to model noise using a learning-based approach called normalizing flows, which I'll describe next. To explain normalizing flows, consider trying to model a complex distribution with some unknown probability density function. Under basic assumptions, there exists a series of invertible transformations G that transform it into a simple, tractable distribution with known probability density function, for instance, a normal distribution. Conversely, we can transform this normal distribution by into a complex one by applying a series of functions f, where the functions are inverses of G. With these functions, we can then formulate the probability density function of the more complex distribution using the change of variables formula from multivariate calculus. This results in a class of models known as normalizing flows, which have been successfully used to model more complex distributions such as natural images and more. So normalizing flows can be used for tasks like density estimation, for instance, by minimizing the negative log likelihood of the observed data, which can be computed through the previously mentioned change of variables formula. At the same time, they can also be used to generate samples from the model as a generative model by sampling from the normal distribution and then applying the forward transformation. In order to model real camera noise using normalizing flows, we introduce a few modifications. We start with the basic affine coupling layer and one-by-one convolutional layers that were originally proposed in the GLOW paper last year at NeurIPS. To adapt this model, we introduce 2 specialized conditional layers, the first being a signal-dependent layer, which models the linear relationship between noise power and the underlying signal. We introduce a second layer further, which is a gain layer, which models the amplification of noise related to the ISO setting of the camera and other more camera-specific parameters. These conditional layers, combined with the previously mentioned affine coupling layers, constitute the overall noise flow architecture. We trained noise flow on real camera noise in raw image space. Given the trained model, we can then generate realistic noise samples by feeding normally distributed noise through the forward pass, along with the underlying clean image. And then the generation also uses the sensor gain settings and the camera identity in order to sample from ISO and camera-specific noise distributions. This generated noise can then be added back to the underlying clean image and processed through the camera pipeline in order to produce a simulated noised image in the sRGB color space. We evaluated noise flow, this model trained on the smartphone image denoising data set, which was mentioned previously. Sample outputs are shown here on the right, show a qualitative improvement over Gaussian and signal-dependent baseline models. Further, noise flow shows a significant improvement in negative log likelihood of a held-out test set, and samples from the noise flow model better match the marginal statistics of real noise samples. In order to demonstrate the usefulness of noise flow model, we consider the application of denoising. Simulated noise is often used to train denoising networks for modern approaches, and we see that training with noise flow generated noise significantly improves performance compared to the Gaussian and signal-dependent baseline. In fact, it actually performs using the real data itself directly to train the denoising network. Code and pre-trained models for all of this is available online, and please come by our poster number 25 for questions and discussion. Thank you.
Hi, I am Ahmed from Carl Zeiss. I'll present the work of bottleneck potentials in Markov random fields, which was done alongside my master thesis supervisor, Paul Swabda, at the Max Planck Institute for Informatics. So we consider problem statement. We consider a problem where the task is to assign labels to each node of a graph. For example, a 3x3 grid graph shown here, where each node has 3 possible labels and the edges model pairwise relationship between the nodes. A possible labeling is highlighted here. The best possible labeling can then be found by specifying a criteria and minimizing it. One such widely used criteria is to represent the cost of a labeling by summing the energies of the individual factors, which is the popular framework of map estimation in Markov random fields. Another criteria, which we call as the bottleneck objective, is to model the cost by its weakest link by taking the maximum over factor potentials. In this work, we consider both the criteria jointly as one optimization problem. An application of such an approach can be in tracking rock layers in subsurface seismic volume. Here on the top row, we see a cross-sectional view through such seismic volumes, where the vertical axis represents depth. Pure MRF in orange fails on this problem as the solution invests in small number of high energy investments to jump to a different track of better overall continuity. Our goal is to penalize such high energy investments by adding a bottleneck term onto the objective. In contrast to prior works containing bottleneck type objectives on MRF, we allow multi-label inference on graphs, give exact algorithm for cycle-free graphs, and a strong relaxation for general graphs with lower bound guarantees. So to model this problem, we add an additional bottleneck term, which is this maximum indicated here, onto the MRF objective, where theta specifies the traditional MRF potential and phi are the new bottleneck potentials. So for cycle-free graphs, we consider chain here. For chain graph, we give an efficient and exact algorithm. We represent chains as a directed acyclic graph containing arcs at A, where each ST path in this graph corresponds to a possible solution. Now, if we do not have this bottleneck term we are considering, the solution can be found very easily by the shortest ST path. But we need to account for this bottleneck term. So for that, we exploit the fact that due to the discrete nature of the problem, the bottleneck term can only contain a number of values equal to the cardinality of the set A. To solve the joint problem, we sort the arcs in A in terms of their bottleneck potentials and incrementally introduce these arcs into the graph. On each arc addition, shortest ST path needs to be found for finding the minimizer. We use dynamic shortest path algorithm to solve this problem in an efficient manner by reusing the distances from previous calculations. For general graphs, we decompose our problem as follows. As an example, we consider a 2x2 graph on the left. First, we separate the MRF and the bottleneck potentials. The MRF is the top one. But inference in graphs with cycles is NP hard, so we further decompose the problems into cycle-free components. For MRF, we decompose the problem into trees, and for the bottleneck, we decompose into chains. The consistency between these variables are enforced by Lagrange multiplier, and we maximize the agreement between the variables by solving the dual problem. Lastly, we recover the primal solution by message passing. So on to some results. As shown here, we apply the approach on tracking surfaces in seismic volume. This is the top view of the surfaces where the color denotes the depth of the surface. On the top left is the ground truth. So in this case, if we see the MRF solution, it is piecewise continuous, which says that it invests in small number of high energy investments to gain a solution which is piecewise smooth. The state-of-the-art heuristic for solving this problem on the bottom left also has some errors. So in summary, we combined the traditional min-sum MRF objective with the min-max bottleneck type objective. We gave efficient algorithms for inference in multi-label cycle-free graphs. We gave a strong relaxation for general graphs, and we apply this approach in tracking rock layers in 3D seismic volumes. So thanks for your attention. For more details, please visit poster number 26. Thank you.
Good morning, everyone. I'm Qifeng Chen. It is my honor to share our work, Seeing Motion in the Dark, on the behalf of the team. Capturing a high-quality video in low-light environments is important and interesting. For example, a dancing video in the dark, seeing the motion of animals in low light, recording a meteor shower at night. However, capturing low-light video is extremely challenging. We cannot have a long exposure time for each frame. Large aperture is not available for small mobile devices. Burst image fusion is not available for video. Higher ISO will introduce higher noise, and no ideal training data for a machine learning model. To address this challenge, we build a dataset with static and dynamic videos. In the static videos, the camera doesn't move and the scene is static, so that we can obtain a ground truth video by simply taking the average of all the frames. In the dynamic videos, the camera can move and the scene is static, is dynamic. There are no ground truth high-quality videos for dynamic environments. Here are some static and dynamic video we capture in the dataset. In our system design, we train a deep neural network end-to-end from raw video data. We employ spatial and temporal denoising to enhance video quality. Our model is trained on static videos, but can be well generalized to dynamic ones. Our model can generate high-quality videos with temporal consistency in low-light environments. For training our model, we first capture bare raw video data. Then we apply some pre-processing steps to enhance the spatial-temporal coherence. Next, we pick 2 random frames in a static video and use a ResUnet to generate 2 high-quality video frames that should be close to the ground truth. Furthermore, we add a self-consistency loss that enforces consistency between any 2 frames. Now we will show some results. The first video is the camera output from a Sony DSLR camera. The second video is the result by simply upscaling the intensity in the raw data. The third video is the result by applying traditional VBM4D. The last video is our result. Here we compare traditional methods, our prior work last year, and our current model. As you can see, our prior work doesn't generate a temporally coherent video, but our current model does. Here we saw a baseline that used post-processing for temporal consistency, but introduced clear artifacts. Here are more comparisons between our prior work and our current model. We saw the results in both indoor and outdoor low-light environments. Here we compare our method to iPhone X and a Sony DSLR camera. And finally, this is a result we have at a birthday party. We first saw the results of iPhone X and a Sony camera. And then we saw our reconstructed video, and now we can clearly see the people in the background. Thank you.
This is work mostly by Jiang, but he couldn't come due to visa reasons, so I'll be presenting for him. This work is about scene flow estimation, and in scene flow estimation we have a stereo pair of cameras and a video from each one, and we're trying to establish correspondences among sets of 4 frames at a time. Starting with a reference frame in the lower left corner, we want to compute correspondence to the future frame of the left camera, but also to the stereo pair frames from the right camera. If we can compute all these correspondences, we can then compute disparity and optical flow at the same time. Now, these problems have both been heavily studied, but the architectures used for them have been quite different, and in this work, we unify the architecture to leverage co-training and shared features. The first step in doing this is to adopt the cost volume representation from PwCnet, which has been successful in representing possible matches in optical flow work. So here we have a patch in the left frame, and it could match any of the possible frames on the right. And then we use a similar representation for stereo disparity estimation, but this time we only have to search over a single line due to the epipolar constraints. Because we're using these similar representations, then we can encode all the images with a fixed encoding represented by these gray layers here with shared parameters during training. So we encode 3 images, the reference frame and the future frame of the left camera, and also the right frame from the, or the right image of the first frame. And once we've established all these encodings, we use different combinations of them as inputs to various back-end components. So the first 2 frame encodings are used to go into the optical flow back-end for computing the optical flow, and the last 2 frames go into the disparity back-end for computing disparity. We also estimate occlusion for the optical flow pair using the top representation, and occlusion for the disparity pair using the bottom representation. Estimating all these things at the same time forces the network to share features and puts a strong constraint and regularization on the learning. And to increase this further, we also estimate semantic segmentations for several frames using a third modular backend shown in blue here, and this provides yet more constraints on the learning. We also use a pyramid pooling module in the bottom 2 components. So I now want to address the issue of dealing with partially labeled data. So we're estimating so many things here that there's no data set that actually has ground truth for all 5 of these outputs. For example, the synthetic scene flow data set has optical flow and disparity annotations, but no semantic segmentation annotations. The Kitty data set has partially labeled optical flow and disparity and semantic segmentations for part of the training images, but no occlusion annotations. So we need a way to train our network even though we don't have all these labels. And to do this, we introduce a self-supervised loss. So for example, if we don't have disparity ground truth, we can use photometric consistency to check and see whether a disparity is approximately correct by using our computed disparities and their photometric consistency. We can also do this for semantic consistency by comparing the outputs of our semantic segmentation. And note that our occlusion estimates are used to eliminate certain pixels from the loss function when they have been occluded. So our Sense and Sense Plus networks are thousands of times faster than traditional energy minimization-based approaches, 3,000 times faster and just a little bit less accurate. We're also 50% faster than neural network-based approaches. We're also a very compact model, 4 times more compact than the best competitor, FlowNet 3, of the neural network approaches. So in summary, 2 of the main contributions are an efficient and compact backend for scene flow estimation and semi-supervised loss to deal with partially labeled data. And I hope you'll come to our poster number 28 for any questions you have. Thanks.
Thank you. Will all the presenters come up again? Is there any question from the audience? There are 6 places to ask questions. Please come up to the microphone. In the meantime, there's a question in the Slido from Idia to the seeing motion in the dark paper. What is the inference time of proposed method?
The inference time. Yeah, so the model is actually based on the one forward pass of the rescue net, and for each frame, it would take less than 1 second.
Okay, please stay in the seat while Q&A session is going on. And is it possible to port it to a smartphone?
Sorry?
Is it possible to run it on a smartphone?
So to use it on a smartphone, I think further optimization of the neural network should be introduced, like maybe a small network like mobile net, so that it can run on smart devices.
Okay.
Okay.
Is there any question?
So I have a question.
Okay, go ahead.
So I have a question for the first paper. So in your denoising example, you show that the model trained with simulated noise from this condition, the normalized flow, it actually outperforms the model that trained with the real noisy clean data.
Yep.
Do you use the same amount of the training data, or, I mean, so I'm kind of puzzled about this result.
Yeah, so by training a separate model to simulate camera noise, we're able to show kind of more variation in noise with the same underlying content. So it's the same raw training data in terms of the clean images, but for each clean image you have effectively a limitless number of samples of realistic camera noise based on the noise flow model. So that's where you get the...
So you generate much more number of training data points, is that?
Yeah, it's done through a standard data augmentation process.
Okay, any other question? Okay, there's another question. Sense to sense paper. Does it also work on monocular video? The last paper? Does it work on monocular video?
Yeah, the question is, does it work on monocular video? Well, scene flow estimation is by definition stereo camera problem. So you could use some of the techniques on monocular flow, but then it wouldn't be scene flow estimation.
Okay, also to you, another question. Do you have any comparison with state-of-the-art optical flow on the accuracy and speed? Do you have a comparison with state-of-the-art optical flow on the work?
Yeah, so I believe at the time of submission we had state-of-the-art optical flow, but 2 papers were published at CVPR 2019 that improved the state-of-the-art in optical flow. So we're slightly behind the state-of-the-art. Is that the question?
Yeah.
Okay.
Okay, to the seeing motion in the dark paper. Does your method work on different light conditions, like blinking bulb in the dark?
What's the issue?
I'm sorry?
What's the issue? What's the issue?
Does it work with different light conditions? Like blinking lights, blinking bulb in the dark, there's a light blinking in the dark.
Blinking?
Yeah. Would that work?
So what are different platforms? Is that your question? What does the method work on different methods?
So the question is, think about a scenario where you have a blinking light in the dark.
Yeah.
Does your algorithm work on that video?
So a blinking light. So
so it looks like a noise, right?
Kind of noise. So this is a very good question. This is a very special scenario. So we haven't tested such a case, a blinking light, but we guess it's probably work. If you look at our birthday party video, so at the beginning it's very bright and then it turns to much darker, and it also seems to be temporarily smooth. Thank you.
Okay, let's thank our speakers again. Thank you all. That's the end of this.